Welcome again. Today we will learn uniqueness theorem. It is very important theorem as far as electrostatic is concerned. So a solution of the Poisson equation whose Laplace equation is special case that satisfies a boundary condition is a unique solution. And this statement is called uniqueness theorem. Okay. The statement is called uniqueness theorem. So to prove this uniqueness theorem, let us start assuming we have a volume here. We have a volume, let us say this is a volume. Tau. Okay. So this complete surface is S naught, in which this volume tau, this complete surface S naught contains the volume tau, and inside this surface S naught, small conducting bodies. Let us say this is a one body S naught, S1, another body S2, and up to Sn. Okay, the small bodies S1, S2, Sn, small conducting bodies. Okay, these are the small conducting bodies. So let us revise. We have assumed that a volume tau is bounded outside by a surface S naught. Okay, and the small conducting surfaces or conducting bodies S1, S2 up to Sn at specific potential. Okay, let us say its potential is V1, it's V2, and so on. Okay, so specific potential for these conducting bodies, we have some specific potential. Okay, now we are starting with the assuming that in contrary to uniqueness theorem, there are two possible solutions. Okay, according to this Poisson, the solution of Poisson equation that satisfy the boundary condition should be unique. Only a single solution is possible, but we are starting with assuming that two solutions are possible. Let us say for this surface we have two solutions, V1 and V2. Okay, two solutions are possible, and these two solutions should satisfy the Poisson equation, which is del square V is equal to minus rho by epsilon. Similarly, this second one, this is the V1. The V2 should also satisfy this equation, minus rho by epsilon. Okay. So let us say this is equation 1. This is equation 2. Simple one. Now we also assume that V1, V2 satisfy the same boundary condition. This is assumption. This we have assumed two solutions. Contrary to this uniqueness theorem, we have assumed two solutions, V1 and V2. So we assume that V1 and V2 satisfy the same boundary condition on S1, S2 and up to S0. Okay, same boundary condition they satisfy. So the potential difference, let us say if we take this term, it is given by Vd. This is the potential difference. Okay. Now if you take that difference, now by using this 1 and 2, by using 1 and 2, equation 1 and 2, and take this subtraction, Vd is equal to 0. This is the case. Del square Vd is equal to 0 now from 1 and 2. Okay. Subtract 1 minus 2. Just 1 minus 2. So del square Vd is equal to 0. Now, so we can say that it implies that Vd is equal to 0. Okay, potential difference on the conducting boundaries is 0. Now let us assume a vector identity. That vector identity is del dot f a. A is a vector, f is a scalar. Will be equal to, this is a vector identity we are going to use here to prove this uniqueness theorem. That will be equal to f del dot a plus, you need to remember this vector identity. So this is the gradient del f. So f is a scalar quantity, okay, without arrow. A is vector quantity. So let us say f is equal to Vd. Okay. F is equal to Vd, as Vd is scalar, and A is equal to del Vd, gradient of Vd. Okay, it is a scalar quantity, we know that. Now put here and solve it, put in this identity and solve it. We will get, put this f is equal to Vd and A is equal to del Vd in this. Let us say this is third. Okay, if you put the values, you will get del dot, this is as it is, value of f is Vd. What is the value of A? Del Vd is equal to, what is the value of A? F. This is Vd. Then this value of A. So del dot del Vd, that will be equal to del square Vd. Okay. Plus, what is A? A is del Vd. So this is del Vd. This is del Vd. Okay. So del Vd dot product, that will be written as del Vd whole square. Okay, so this is what we get by putting the value of this f and A. So now I'm taking another page. So now let us rewrite this del dot Vd del Vd is equal to Vd del square Vd plus mod del Vd square. Okay, now this term del square Vd is 0, so whole term will be equal to 0. Take the volume integral both side. If you take the volume integral both side, del dot Vd del Vd is equal to volume integral of this del Vd square dV. Now apply divergence theorem here. Divergence theorem is used to convert volume integral into surface integral. So that will be tau. So by assuming this as a single term, so that will be equal to closed surface integral of del Vd okay, or ds is equal to tau del Vd square to dv. Okay, now let us assume that the surface we have assumed a very large surface, we have assumed very large surface. Okay, and the surface contains the very this surface is not we have assumed, which contains a different surface S1 up to Sn. We have assumed that. Okay. Now we assume that this surface S naught as a surface of very large sphere. This is a very large sphere having the radius r. Okay, we are assuming that this S naught is very large surface having a very large radius r. Now we know that this potential V is directly proportional to r. If this is directly proportional to r, what will be del V? It will be directly proportional to 1 upon r square. And this surface area, if you want to solve this ds, surface area of that sphere will be okay. This del Vd is 1 upon r square, and this ds, the surface area, will be equal to 4 pi r square. So surface area is 4 pi r square, and this term v del v will fall as 1 upon r cube. Okay, so this whole term will fall as a 1 upon r cube. This will increase as a r square. So this is decreasing as a 1 upon r cube. This is increasing r square. So resultant will be 1 upon r. So the complete term, this complete term will fall or will vary as 1 upon r square. Will be directly, or we can say this whole term will be directly proportional to 1 upon r. If this r is very large, if r is very large, so this whole term will be equal to 0. For this, if r is very large, this whole term will be equal to 0. So we can say that it implies that this whole term will be equal to 0. So this equation only is satisfied when this Vd is equal to 0. So when Vd is equal to 0, it implies that V1 is equal to V2. So we have only one solution. We have proved that V1 is equal to V2. So this is the uniqueness theorem. So for the solution of a Poisson and the Laplace equation that satisfies the given boundary condition is unique. Okay, we have proved that. Thank you.